Hello all. I am Sarah Kinkle. I'm the Partnerships Manager in the Innovation and Entrepreneurship Unit at UTS. And on behalf of UTS and Q-CTRL and the City of Sydney, we are so delighted to welcome you here tonight to our panel, Building a Strong Quantum Future for Sydney. Before we start, I do want to pay my respects to the traditional custodians of the land on which we stand, the Gadigal people of the Eora Nation, and to acknowledge and pay my respects to their elders past, present, and emerging. So we are so thrilled here at UTS to be participating once again in the City of Sydney's Visiting Entrepreneur Program. This is a program that's been ongoing since 2017, and in that time there's been over 70 events, over 90 partner organizations, and I know another 13 events this year. And it's just such a fantastic program that brings together the best of what Sydney has to offer and connects it with really the best of what the world has to offer. So it's such an exciting global program, and it's so fantastic that it's been able to continue even in these trying times. And this year's theme has been about the transformative power of deep technology, particularly about quantum and biotechnology, and about the new possibilities that these technologies will unlock for us. So before we do get started tonight, I also wanted to alert those of you who are interested that, of course, this is one of a series of events, and there are more upcoming. One in particular I wanted to draw your attention to is taking place this Thursday on the 10th of June from 6 to 7. It's free, it's online, words we all like to hear. And it's titled In Science We Trust. You'll have the opportunity to join Alana Wisby, the CEO of Oxford Quantum Circuits, and a panel of thought leaders exploring the many dimensions of ethics in a technological world. If you are interested in registering for that, you can go to city.sydney/VEP. On that note, our hashtag for tonight is #BEPSID, which weirdly did not get updated in that slide panel for the people in the room, but it is #BEPSID. So we are here tonight to talk about building a strong quantum future for Sydney, to talk about why this industry matters for Sydney and Australia, about the amazing foundations that are being laid now and the great work that's being done now today, and about how we can continue building that momentum towards the future. So without further ado, I'm going to hand over to our panel's moderator, Dr. Michael Hush, the Chief Scientific Officer of Q-CTRL, to introduce our panelists and take us forward. Thank you, Michael.
Thank you very much for that introduction. So yeah, today we're going to talk about building a strong quantum industry for Sydney. Hopefully we're going to address some really important questions about what's going on right now and what we can do to do better as a city. I'm Dr. Michael Hush, so I'm the Chief Scientific Officer at Q-CTRL. I currently look at all of the research going on at that company, and I've also actually spent some time as an academic in Australia. But today is not about me, I'm just the moderator. It's about our fantastic panel, which I'd love to introduce now. So first we have Chris Ferry. He's an associate professor at the Centre for Quantum Software within the University of Technology, Sydney, where we're currently located. He obtained his PhD in quantum information from the Institute for Quantum Computing at the University of Waterloo in Canada. He specializes in the theory of quantum characterization and control, and many of his theoretical protocols have moved into practice, being implemented in laboratories worldwide. Chris is a gifted scientific communicator, having published over 50 children's books on science, which have been translated into 15 languages and have been sold to more than 5 million copies worldwide. I have, of course, here one of his wonderful books, not set up at all, Quantum Computing for Babies. I highly recommend that you take a look at it at your closest bookstore, if they still exist. Then Chris is a creator of many of our educational innovations in quantum science in both the classroom and out, and he is actually a quantum education advisor at Q-CTRL. Next on our panel, we have Biljana Rajovic. Biljana leads the development and implementation of Sydney Quantum Academy's engagement strategy. She has worked in both large global organizations, boutique firms, and startups in New York, London, and Sydney. She has more than 20 years experience spanning investment banking, investor relations, and software development products. Prior to SQA, Biljana was on the leadership team of an Australian AI startup, leading corporate and technology partnerships, GTM execution, and capital raising, and Biljana received her MBA degree from Cornell University. She also has a book coming out. No, that's but she's got a great amount of expertise, both outside of simply the academic sector, but also crossing between the two. So it's really great to have you here as well. Next, we have Nathan Langford. Nathan Langford is an ARC Future Fellow and Associate Professor in the Faculty of Science at UTS, where he leads a research group on quantum circuit science in UTS, and a new state-of-the-art cryogenic facility for studying superconducting quantum processes. Nathan is also in the Center for Quantum Software and Information. After graduating from his PhD at the University of Queensland in 2007, Nathan worked in leading experimental quantum science research groups across Europe before returning to Australia to take up a lecturing position and future fellowship at UTS. He has a broad background in quantum technologies, ranging across widely different experimental platforms, as well as theoretical research. And his research currently focuses on superconducting quantum processes to simulate exotic physical systems. Nathan is also a keen science communicator and was once runner-up on I'm a Scientist, Get Me Out of Here. It's great to have you on the panel, of course, Nathan. Superconducting qubits are such a big topic as well in quantum computing, so it's great to have that expertise. And next we have Michael Biersick. He is the CEO and founder of Q-CTRL, a quantum technology company, and a professor of quantum physics and quantum technology at the University of Sydney. In his academic position, he leads a research team as chief investigator in the ARC Center of Excellence for Engineered Quantum Systems, exploring the role of control engineering in quantum coherent systems. Michael earned his undergraduate degree from the University of Pennsylvania and his master's and PhD from Harvard University. He has a research fellowship in the Ion Storage Group at NIST Boulder and has served as a full-time technical consultant to DARPA, helping to steer government investments in quantum information and advanced computer architectures. Michael is also a South by Southwest and TEDx presenter alumnus with a multi-time Australian Museum Eureka Prize nominee and winner. Great to have you here, Mike. And finally, we have Simon Devitt. Simon Devitt is a senior lecturer in the Center for Quantum Software and Information at the University of Technology, Sydney, and co-founder and managing director of the quantum technology consulting firm HBAR. Completing his PhD in 2008 in quantum engineering, he has held research positions at the University of Cambridge, the Japanese National Institute of Informatics, Keio University, and Japanese National Lens Riken. His expertise is in quantum computing and communications architecture design, quantum error correction, and quantum algorithm compilation. He has worked with numerous corporations and VC firms on their expansion into the quantum technology space and advised multiple government agencies on multi-award $1 million R&D initiatives. In 2021, he was awarded the inaugural Warren Prize for the Royal Society of New South Wales for his service to global quantum computing development. Great to have you here as well, Simon. So we clearly have quite a range of expertise in the panel, from everything from industry through to academia to the bridges between. But enough from me, let's say some things from the panel. So the first question, which I'd like to get perspective from both Mike and Simon, who might give us the kind of experimental versus theory side, is what is quantum technology?
I assume this is on. Oh, yes, it is. Everyone's holding quantum technology in their pocket. Every single phone you have, every single watch you have, everything's all based on quantum technology. We sort of make this distinction now. We try to sort of tell people or sort of lead them into what quantum technology is by making the distinction of the quantum technology that exists in the 20th century and the quantum technology that we're all trying to build now in the 21st century. So 20th century quantum technologies you're all familiar with. Transistors, they only work because of quantum mechanics. The laser only works because of quantum mechanics. Medical imaging, MRIs, only work because of quantum mechanics. But they're working basically through the quantum mechanical effect of billions upon billions upon billions of atoms. The actual properties that they have and how these things act as, say, switches in the context of transistors occurs because of quantum mechanical properties, but we're not exploiting quantum mechanical properties directly. Whereas the second generation of quantum technology that we all work on, whether it's computing, communication, sensing, what have you, this is all based upon exploiting the actual rules of quantum mechanics at the subatomic level, whether it's atoms, whether it's particles of light. And that opens up a range of possibilities in computing, sensing, and communications that just isn't possible when you think about classical transistors or the digital world that came about in the 20th century. This is why it's so interesting and so important in this century that this technology is actually moving forward, because the first generation of quantum technologies led to the digital revolution. So what's the second generation of quantum technologies going to do?
Hello. Let me give a couple of additional perspectives. Obviously, everything that Simon has said is almost verbatim what I would say in this kind of setting, except much more eloquent than I would. I think here's an analogy to try to bring home that point. the way we build technology today, by analogy, is a little bit like building a sand sculpture. We take a giant pile of stuff, and if we learn the right rules, we can shape the stuff into the form that we want. Whether you're a really skilled artist and you shape that into, you know, a sculpture of an amazing castle, or Freud and his patient in a sand sculpture, you know, you're always still using the properties of the big pile of stuff. And so it shouldn't escape your understanding that if instead of looking at the giant pile of stuff and what you can do with it, if instead you look at the single grains of sand, you'll see that when you look closely enough, it's not just a homogeneous pile of tan sand. Instead, you see that there's a new level of complexity that was just not visible to you when you only look at the giant pile. When you look at the individual grains, you see that some are seashell and some are stone, some are transparent, some are opaque, some are rough, some are very smooth. And absolutely none of that is visible to you when you only look at the giant pile of stuff. And so the transition that we're making, that Simon alluded to, of what we talk about now in the 21st century of quantum technology, is about looking at the individual grains of sand and building technology from the individual grains of sand. Those are the individual quantum mechanical systems. In the 1980s and the 1990s, we learned that you could get down to isolate individual grains of sand in this analogy, individual atoms, individual elements of electrical circuits that obey the rules of quantum mechanics. And what we've been working on since then is putting that phenomenology, all the complexity we find when we look closely enough, to work. Now, let me expand one step further on Simon's comment. In addition to things like lasers and transistors and computers, there is actually one bit of quantum technology that meets the definition that I think all of us would use for this 21st century or second quantum revolution, which has in fact already changed your life, and that is GPS. GPS works because of atomic clocks. Atomic clocks give us a very, very stable tick that comes from inside the atom. And we can only access that tick if we use quantum mechanics to do so. Now, just think about how GPS has changed your life. Did you get here using Google Maps? Did you use an Uber? Think about all the location-based services that are tied back to this first true application of what we would collectively call quantum technology. That's just the first thing that we thought of, right? And now our interest and our excitement is about everything else that we can build from there.
Those are some great answers. And again, I think that's the first time I've heard an explanation of quantum technology without jargon like entanglement, superposition, or coherence. So great work there. Trying to continue that theme of accessibility so everyone has an idea. I think another really great way to understand how quantum technologies affects us is talk about applications. So for the rest of the panel, would you mind telling us about what particular quantum technology has an application that you're really excited about? Nathan, do you want to go first?
All right. Okay, so I think for me, the most exciting quantum technology applications will be those that arise out of quantum computing, and in particular, to use quantum computers to model the behavior of really complex physical systems. So it turns out that modeling a large chemical or biological molecule or an exotic material like novel superconductors is actually something that's really super hard to do on a traditional computer. And in fact, a significant fraction of the world's annual supercomputing capacity gets used to do exactly this sort of in silico molecular modeling every year. But because quantum physics underpins and drives a lot of the key properties of these sorts of systems, it turns out that quantum computers are actually really well placed to take up this challenge and in fact do it a hell of a lot more efficiently than a traditional computer. And the potential payoff here is really huge. Imagine if you could find a more efficient way to make fertilizer than the century-old Haber process that's still in use and consumes some few % of the world's global annual carbon budget. Or imagine if you could dramatically reduce the amount of time and money it takes to develop and test new vaccines and new therapeutic drugs by using a quantum computer to artificially test, to simulate and test these new potential molecules and chemicals that people want to use in these contexts. And in doing so, cut out a huge amount of the expensive, labor-intensive, and necessarily hit and miss lab synthesis and testing that costs a huge amount of money for the pharmaceutical industry every year. And that's the sort of area where we hope quantum computing can take us.
So Biliana, are you also excited about quantum computing or a different technology?
What I'm excited about is a little bit of what Nathan touched on. Something is near and dear to my heart is the life sciences industry and the potential of faster drug development and the trickle-down effect that can then have on the society for people getting life-saving treatments or affording life-saving treatments in time. And also the idea of potential personalized medicine therapies.
Chris, what are you thinking?
Yeah, so I mean, obviously I agree. I think the typical answer you hear is that quantum computers will be used to solve kind of abstract problems, like maybe we'll multiply matrices faster, or it could help with machine learning. And I think that may be true, but it's these spin-off effects, like when the first atomic clock was invented, nobody thought that what we really want is Uber. Nobody thought that that's what we were planning on doing, right? So, and it's not us, it's not the people deep into the research that it's going to come up with those ideas. It's going to be the community of people that come into the field afterward or now that come up with these ideas and applications that we could never dream of because we're deep in the weeds trying to multiply numbers faster. And one of the other points that I wanted to make about physics, if you think about what we're trying to do, we're going to build a device, and it's going to be a device that we can't really explain the inner workings of in great detail. A quantum computer will be a black box, and you can't look in the box. If you look in the box, you'll break the computation. So what's in the box will be a new state of matter, something new in the world that's never existed before, that we will have created. And I think that's a really interesting thing to think about, that a lot of the technology that we've created over the past was to help us go out and explore the world. And these technologies were great at going out and seeing what was already there. Whereas now we're going to build and design the world at the most fundamental level. And what we find there may be incredible. It will certainly be a paradigm shift in all of science. So that's what I'm most excited about.
Yeah, maybe I just wanted to pick up one extra thing to drive home this point about the unknown applications being maybe the most exciting. The first digital electronic computer was called the Eniac. That was at the University of Pennsylvania. It's the first computer that really looks like the computers we use today. It had digital encoding. The encoding was electronic. Now the hardware was different, obviously. It was publicly released in 1947, but the spec for it was like 1943. That's when the money started coming into Penn to build it. Anybody know what the application that they proposed was? It was only one. It was only one application for the world's first computer, first electronic digital computer. Calculating artillery shell trajectories. That was the only thing anybody thought was valuable enough to build what is now the information revolution, right? And so I think we have really exciting ideas about things to do with quantum computers, but I think they're going to look pretty silly in 30 or 40 or 50 years when we start actually running these things at scale.
Just following up on that, I think one of the really interesting things about exactly this point with quantum computing is that quantum computers, as Chris was saying, are kind of the ultimate in complex matter systems. And in some sense, one of the big challenges about building a quantum computer is you can't know what's going on inside. otherwise you break it. And for a quantum computer to be interesting, it has to get big enough that it's doing stuff you can't do on a traditional computer. So kind of by definition, if we build this quantum computer large enough to be interesting, we are not going to be able to easily predict and know what is going to happen with the understanding that we have at the moment. And this is going to require a completely new way of looking at it, a completely new breed of programmers and data analysts to both control and then analyze what's coming out of these machines. And that's going to be, I mean, that's something that we can't possibly know about. Like that's something that's going to happen and emerge over the next few decades, I guess.
Yeah, so there were some amazing applications there, from health to other unknown applications as well. I'm going to ask this question to the two people who have companies which are based around the quantum technologies. I'm sure this is a question you both relish and loathe, but when will we see the benefits that we've been just described? What is the time horizon for these outcomes? That's to Mike and Simon.
Well, I mean, Mike already alluded to it. We already have seen the benefits when it comes to atomic clocks, timing standards, which leads to GPS. Now, hidden within that question is, when are quantum computers going to display benefits? That's what people are really asking. When is a quantum computer going to be something that's going to be useful for any kind of commercial or scientifically useful application? Again, it kind of misses the point, because building a machine that can give Summit, the supercomputer at Oak Ridge National Labs, a run for their money in any computation, is that a benefit? I think it is. This is the Google supremacy result that was done a couple of years ago. 50 quantum bits gave the world's largest supercomputer that is used for nuclear weapons calculations a run for its money. I think that's a benefit already. It's already telling us how to engineer these systems, and it's now gotten to the stage, you know, I've been in quantum computing for about 15 years now. It's now routine. It used to be to build a qubit in the lab was a major effort for a new academic that was starting up. These days, you can order them online, just about. Okay, that's a benefit in my mind. When the systems are going to get large enough that they're going to become commercially competitive, that Pfizer or General Motors or GE is actually going to be buying supercomputing time on quantum computers to do their calculations, I mean, you get a range of answers depending on who you're talking to. If you're talking to people with companies, they'll put the timeline a bit shorter than people who are in academia, but nobody knows. Nobody really knows. We're hoping to see good commercial applications, or at least demonstrations of the building blocks of commercial applications within this decade. Now, I don't want to speculate anywhere beyond that. I mean, who the hell knows? We could all be gone by the end of this decade. So, you know, but I'm a pessimistic guy.
Are you really? I think maybe a different way of phrasing the question is like, when do we expect some company to make ungodly amounts of money from the work that they're doing building some quantum thing? You know, Simon is quite right that you get more pessimistic answers from academics on average. You get more optimistic answers from industrialists on average. You know, it's a little bit like picking stocks. The reality is nobody knows if it's going to go up or down. Nobody exactly knows, as Simon was saying, what the timing is going to be. I mean, based on the pace of progress that I have seen, based on my time building quantum computers for the last 21 years and the time that I spent in government, like supporting this, I legitimately think that we're getting to the point where in the like 5 to 8 year time horizon, we're going to start to see quantum computers that outperform you know, conventional machines for tasks that people care about, right? There are scientifically interesting tasks like the quantum supremacy experiment that have indirect benefits. And then there is the like, when do I design a drug on a quantum computer? You know, that threshold, I think, is in this 5 to 8 year timeline. But what to me is also exciting is that everything we're learning about building quantum computers actually falls into another category of applications that we don't hear as much about. It's not as sexy, called quantum sensing, which is taking the fact that quantum hardware is really, really fragile. One reason it's really hard to build these big systems is that it breaks very easily, right? It just turns back into garbage. Well, you can kind of turn that on its head. You can use that as a benefit, as a technological capability to detect very small signals, in particular, very small magnetic signatures. Maybe you want to do mining exploration, very small gravitational signatures. Turns out you can measure ocean currents directly. You can map ocean currents with gravity from space, right? And so quantum sensors that leverage this weakness as a strength give an application or give an opportunity for applications that deliver on nearer timescales. And the reason is that, very coarsely, a quantum sensor is a lot like a 1 quantum bit quantum computer. It's like a quantum computer with one element. And we're really good, as Simon was just saying, even at making them in like the most junior academics intro lab. They can make a qubit, and we know a lot about how to manipulate them and operate them. And so I'm particularly bullish on this next few years about the emergence of quantum sensing applications for a range of activities. And in particular, we focus in Q-Control on navigation, building new kinds of navigation technologies that work in the absence of GPS. So it's called dead reckoning navigation. Measure where you're going and where you are, even without a GPS beacon.
Right. I think that's great to hear about the timelines. I think we've established pretty clearly now what the quantum technologies are and their applications. Let's bring it down to a smaller scale now and talk about the city of Sydney. I think this question is best for Biljana. So you've got expertise at the Sydney Quantum Academy of sitting in between industry and academia. So what would you say are the current advantages that Sydney as a city has in the quantum space?
Yeah, so I think one of the things that many people don't realize that Sydney has one of the highest concentration, if not the highest concentration of quantum scientists and talent in the world, ranging from experts with decades of experience to early and mid-career researchers to PhD students, and also the emerging talent at the undergraduate level. Last year, UNSW was the first university in the world to offer a Bachelor's of Engineering undergraduate degree in quantum engineering. And then you have the organization like the Sydney Quantum Academy, where the quantum community is banded together with the New South Wales government, to show their support of continuing to develop this PhD talent. Plus, we are looking for ways to actually help upscale the entire corporate workforce at various levels. And none of this would be possible if we didn't have this deep expertise on the ground.
Yeah, I think that's a really good foundation. And I'll kind of broaden out the question to the rest of the panel, really to the core question that I wanted to ask today about how we as a city of Sydney can do better to grow our quantum industry. So this is a question for everybody. There's a lot of emphasis on industry-academia collaborations in policy. Is this the right end result we should be targeting? Are there good examples worth emulating out there already? And how can Sydney do better? You want to volunteer to go first, Nathan?
Yeah, this is a really interesting question. I think for me, quantum technology is something that really exemplifies the very definition of a deep tech development field. And by deep tech, what I mean is a field which really combines critical elements from bleeding edge research science and big tech scale engineering development. And that means that on their own, a research scientist would really have no hope of trying to build a quantum computer without the sort of the scale and the investment and the process optimization that industry can help bring to the table. But at the same time, you can give us all of the undergraduate engineering graduates in the world, and without the world's best research scientists being able to bring those conceptual shifts and the really transformative out of the box innovation that you get from pursuing those tangential research paths, the industry actually really struggles to follow. When you're developing a product, it's really hard to kind of follow all the tangents. And that's absolutely critical in this space at the moment. And we're really seeing exactly this interaction at the moment in our field. What started as basically an academic pursuit in the mid-1990s is now getting huge interest from industry around the world. And I think in my field, in my particular experimental area, there's a really good example of this, which is that John Martinez at the University of California, Santa Barbara, he's really one of the key founders of the area of superconducting electronic circuits for quantum information processing. And about 10 years ago, Google effectively adopted his entire research group into Google.
Bought.
Yeah, bought. And you know, they were already doing amazing science in the Martinez group. But since they joined Google, it's been really exciting to see the transformation they have taken to the next level, where the sort of stuff that they can do is really is changed by the fact that they're now embedded in the sort of massive corporate machinery that a company like Google can bring to the table. But even though this is kind of the fairy tale story of academia industry collaboration in some sense, I guess I would say that maybe this is not the example that we want to follow, that we should be trying to follow. I mean, let's face it, how many Googles are there? How many groups, academic research groups, are there like John Martinez's group? This is a really, really hard thing to replicate. So actually, I think I would argue that one of the things we should be trying to do really, really hard, especially in Sydney and around the world, is that we should be trying to really strongly support the academic groups at this point. Because as industry expands, they are going to need, industry needs people, and that's great for all the academics and research students have possibilities to go off and join really exciting companies and stuff. But as industry expands, so is going to expand their need for more talent. And if we don't really strongly try to expand the support for academic research groups, then what starts as a healthy flow of people from academia to industry could become an exodus that could be really damaging. And I think that, as I said before, deep tech really needs the slightly less constrained research paths and the more out-of-the-box thinking that you're able to pursue as an academic researcher. And then that's a really critical thing to bring to the table for quantum technologies and quantum industries for the coming decades. So I actually think we should be really strongly trying to expand our support for young, up-and-coming researchers in the academic space. Yeah. People who, and the last thing I'll say is the people who will be making the discoveries in 10 to 20 years that will be really profoundly changing the path towards quantum computing, they're not going to be people, I don't think, who are currently working in the big current groups now. They're going to be people who've come through groups that haven't even been established yet. And this is why I think it's really important to support the young people coming through.
Do you want to give a counterpoint for that, Mike, from your industry's perspective?
I will give a point from an industry perspective. It is not a counterpoint. I think, so the first thing is, Nathan hit the nail on the head with one thing, but I wanted to give some context. Why does this question come up a lot? It's because this is a policy question. What should the government be doing? What should the government be investing in? And right now, the government in Australia is pushing very hard on supporting industry academic collaboration, right? Now, my personal view is that this is focusing on the means and not the end. The end that we want is a vibrant industrial, R&D and technology sector where science turns into products and outcomes, right? That's what we want. And I think we've narrowly focused on one mechanism to support that. Now, the other thing is you don't make industry policy by looking at Facebook, right? You don't look at that and say, oh, we're just going to make more of that, right? You may say, well, we'd love to have more companies of that scale. We'd love to have more companies that are as successful, have the same market cap. But you don't look at the outlier and say, we're going to make policy around that. You try to make policy that has broad-based impact. And in my view, when we look at industry and academia and collaboration, in particular in Australia, the policy perspective is quite simplistic, and it's really like on a scale of like smart to dumb. You have academia, then there's this like clear threshold, and then you have industry above. That's the policy perspective. Industrialists, they're dumb. Academics are smart. But academics are also, if you make another axis that goes the other way, from like impact, high impact to low impact, it goes the opposite direction. Academics have no impact. Industrialists have big impact. It's completely stupid, but this is the perspective. And so I think we need to change the narrative to make sure that people understand that it's not just like you take some people from the smart category and some people from the not smart but high impact category and you put them together and everything gets fixed. Instead, we have to look at like how different industry is. Yes, you have rent seekers who make money by investing in property just before there's a development application that builds a train line nearby. You have plenty of that, and we can't fix that. But you also have companies like Simon's company, like my company, that are research driven. And I would say the reality is we don't, in air quotes, we don't need industry collaboration, just like successful research groups like Nathan's don't need industry money, right? There can be circumstances where it's beneficial, but just saying, well, all we're going to do is focus on the engagement and the collaboration part, and then everything else will take care of itself. It ignores reality. It ignores the fact that these programs like the CRC scheme have been around for decades and have not fixed the problem. The ARC linkage program has been around for a number of years and has not moved the needle at all on improving commercialization outcomes. So, you know, they talk about the definition of madness. This discussion falls into that category. So I think we need to elevate the level of discussion and look at a diversity of ways to support both the industrial research and the commercialization, as well as providing robust support for fundamental exploratory science.
I mean, Michael's completely right in this. There is a real problem at the policy level as to industry engagement. We don't care how, we don't care why, we don't care any kind of details. It's just industry engagement. And it ends up being a focus of academics as to who you can engage with and what companies you can deal with. But in the quantum space, I always like to point out when I'm talking about this is that while the industry side and the corporate side and the VC side might be the most visible, it's not the most heavily invested part of quantum. Government still vastly outweigh the funding that's coming into the quantum sector. I mean, just in the last year, we've had the French announce a $3 billion initiative. We've had the Germans announce a $2 billion initiative. We've had the Dutch announce a $1 billion initiative. The Dutch, this is a country of the same size as us, the same GDP as us, the same very, very good talent base as us, and they've already got a $1 billion European Union international initiative. But they still thought, well, we'll throw another $1 billion into this. Australia did a very, very good job in the late 90s and early to late 2000s, really punching above our weight. That's why we have such a strong talent pool in Sydney and throughout the country. But as Biljana said, Sydney's got a very, very high concentration. That was because of Australia making a dedicated choice early on to say, no, we will fund this. But the rest of the world is ramping up. The rest of the world is saying, no, we're going to go 10x. We're going to go 100x on top of the funding that we put in the early 2000s. And Australia is sitting here twiddling its thumbs. Now, the industry only comes, the startups only come when you're sitting there and you've got a good talent base that are sitting there and you've got basically a surplus. And we don't really encourage spin-outs very much in Australia. I mean, the quantum spin-outs, you know, not counting HBAR because we don't do technology, we're a consultancy firm. But of companies actually building stuff, there's Q-CTRL, there's SQC, there's Quantum Brilliance, Quintessence doing communications, and then a few companies doing peripheral technologies, sort of support technologies or device technologies. That's quite bad considering the impact that we had in the early 2000s. And if you just look at the Australians scattered far and wide, I mean, talk about industry collaborations. I mean, it's industry poaching. I mean, the University of Sydney lost 2 faculty members just in the last 6 months to Amazon. Who knows if that's the end of it? That's the industry collaboration that we're seeing. Now, for the researchers, it's great. You go join one of these big corporates, you get a salary bump, you might get to go back home. But certainly I don't want that. I'd like it to happen here in Sydney because I like Australia. But I'd much rather see us grow as the rest of the world is growing on this stuff, and then foster these kind of spin outs or these industry collaborations just as a natural consequence, rather than insisting that without any government support, everyone must have an industry partner, which just doesn't work. I mean, at UTS QSI, for example, we do quantum algorithm development. Nobody in our center is really keen on industry collaboration because it doesn't match our research programs. The people who are doing algorithm development at UTS are not really interested in what's going to happen in the next 3 or 4 years in optimizing financial portfolios. That's not their interest. That's not what they're trained to do. So there is this issue.
Can I just say, and that's okay. We need people who think on 30 and 40 and 50-year timescales. I mean, I run a company. I'm an industrialist. I have a short-term time horizon. And I need people like Simon who say, what are we going to do with this technology that you're enabling in 40 years, right? If we don't have this diversity of timescales in our R&D portfolio, everything falls apart.
And what's really important to add to what Simon said is that the people at UTS who are working on this stuff, they're like world leading in this area. This is not people who are doing something that's not considered important or like they are really at the head of the game, but it's just they're playing a game, as Mike said, that's 2 decades down the time horizon.
Chris, did you want to make a comment? You are one of the people that they're talking about right now, as someone who's at UTS working with industry today.
Yeah, I think that something practical for me, and it sounds like it would help with a lot of these problems, is bringing in students at the undergraduate level. I don't have enough PhD students to send out into industry. How do I get them? Well, right now they can't come from overseas. So where are they going to come from? They need to come from Australia. So we need to get high school students, people that want to upskill, into our undergraduate programs. UNSW has an undergraduate program in engineering and quantum computing. UTS has an undergraduate program. You can get a Bachelor of Computer Science with a major in quantum information science at UTS. We need people into these programs, and where they will go from there, they might come and join our research groups. They might go and join companies, but we just don't have enough of those people there. So we need to somehow encourage, incentivize people at that low level. And this isn't going to solve the problem today or tomorrow, but an undergraduate degree is only 4 years. So we can start to look forward to this problem being solved 4 or 5 years from now if we can get students today into these programs.
And for those students, it's probably worth saying that, I mean, quantum technologies is, it could be a bit like the NASA space program. There's a lot of stuff that can come out of this. Even if you train and you get a degree, Bachelor of Computer Science in Quantum Information Science, that doesn't mean that that's the thing that you have to do for the rest of the career. You're going to be getting a huge amount of really useful skills that will be, we don't know what the spin outs are going to be that are going to arise from this massive research program that's happening. So there's a huge horizon there.
Yeah, I mean, I don't think you can find an example of someone who got a degree in quantum computing and didn't end up being successful. I mean, getting a technical degree is pretty much a guarantee for, employment or probably happiness. I think we're all pretty happy. I mean, yeah, we all got degrees in quantum computing 10 years ago. I think some of us were
too philosophical about the decisions I've made in my life. I've noticed a theme that's developing. We really are talking a lot about how industry and academia are connected through the talent that goes through. So I have another question for Biljana. How do we build wider quantum literacy and the right talent pipeline to support both researchers and entrepreneurs?
Yeah, so I think you can end up with a wide spectrum of quantum literacy. And I think we have to, as educators, think about how can we develop the right talent for the right content for the right people. The CEOs at the CEO and the board level, what do they need to know in order to understand how this emerging technology is going to transform their industry, their company, their workforce, and how can they continue to drive change within the organization? The classical developer, how do they need to be retrained to have the right future technical skills? people working in quantum adjacent industries, or people working at companies as Q-CTRL who are not quantum scientists, but who are always working with them. What level of knowledge do we need to get them at? And then how do we deliver this? What's the right mixture of in-person teaching versus online? How do people ingest knowledge and information nowadays? Look, it's definitely a tall order for the educators, but I think that's okay. This is a long-term game. And then to your point earlier, in terms of we need to look at the top of the funnel. How do we entice people to actually study these subjects? And I think one of the things we need to do is we need to demonstrate, as much as you don't want to work with collaborative industry or looking at near-term.
I did not say I didn't want to. I
looking at
collaborate with
near-term
industry all the time.
Well, we need to make clear connections between what you're studying today, and there's going to be a job there waiting for you 4 to 5 years from today, not just in academia, but with industry. And for that, we need these collaborations to actually explore these future use cases so that companies are going to understand what are the skills they need to look for and hire for 4, 5, 10 years from now. So
yeah, I'll pick up on that, and I'll actually highlight a relationship that Q-CTRL has with Chris. I mean, it was highlighted before that Chris is a quantum education advisor. Chris is an academic at UTS. Q-CTRL has a lot of talent in web development and professional software engineering and back-end engineering and product design and user experience and user interface design. And we decided to get together and build something kind of new and different. And that is an ed tech tool that leverages the best practice in product design and user experience, but is informed by education and education-focused research. I mean, maybe do you want to say something about some of the content development that we're doing together?
Yeah, so I think this is a great point, and I think it hits upon a lot of things. Like one of them is that when we think about the collaboration between researchers and industry in deep tech, we imagine like there's geniuses that are going to go behind some lab door, and they're going to, that's the only way in which we could collaborate. But no, there's lots of ways to collaborate, and one of the ways in which we're collaborating is providing new innovations in quantum education. And before I said, I want students, but that's putting my academic hat on, because that's what we do, right? We work at a university, and we need students to pay fees so that the university can pay our salaries, but also to help us do research. That's just one side of it, right? But everyone can and should be educated in quantum technology, just like I teach my children how to code. I teach my toddler how to code with a little robot and a little thing, right? You could have said the same thing about conventional computing 50, 60 years ago, saying, it takes experts and people with a lot of expertise to do this. 70 years later, we're now teaching toddlers to do it. So we can do this, but we need innovations. And that's what we're doing at Q-CTRL with this collaboration, is coming up with new innovations to teach not just students, not just experts, about quantum technology and quantum computing.
Yeah, an important point is that we're trying to leverage the expertise of both sides. Chris is an expert in the science communication part. I mean, he's obviously an expert in research as well, in the content, what should be taught, how do you teach it in an effective way. We're experts in building products, right? And I can tell you from my time in universities dealing with web interfaces like Sydney Student for online student management, that universities are not good at product development, right? They're not good at software engineering. And so this is an opportunity where we bring kind of the best of both worlds, and then we end up testing the new technical product in an education setting. We'll be using it in UTS's coursework in the future, right? It's a really cool example of a collaboration that is more than just, we buy your science.
Maybe,
or we buy your education product, right?
And maybe there's one last thing that we can add to all of these. I mean, these are all great points. But one thing that's particularly important for Sydney, I think, so I'm going to use a buzzword. And if you've ever written a grant application or something, then you will know this buzzword is vital importance to your survival. And that's interdisciplinarity. And it gets applied everywhere. But the thing is that quantum technologies is one of the most interdisciplinary fields that's out there. Okay, vital to our survival. Started out as mostly physicists, but now we have engineers, we have computer scientists, we have mathematicians, we have chemists, we have financial analysts now getting involved. It really is massively multidisciplinary. And one of the super exciting things about Sydney is that we actually cover a huge amount of this space in one place. We have experimentalists and theorists. We have people from lots of different experimental platforms. We have computer scientists, mathematicians, chemists, physicists, engineers, all working at world-leading levels in this area. And one of the key things, if you want to get people involved in the industry and bring in the talent and educate, improve the quantum literacy, is you have to talk across these disciplines. And one of the really huge challenges when you're working in the science research space is when you have to be a physicist and start talking to a microwave engineer, you're using completely different language. And we're getting this we're all kind of getting used to this, but it's happening again as you go to academics start talking to industry people, as you get the education people talking to the web designer people. Each one of these situations requires building a new language to talk between these different cultural groups, if you like. And this is something that I think we need to do, and it's something that in Sydney, I think we're really well placed to make a really great stab at.
Yeah, it's really about, I guess we're hearing, it's really about the people and the talent that you have. And so I guess this brings us to, we're almost at the end of the official questions, and then will be a second section where everyone in the audience has a chance to ask some questions. But there has also been a really big challenge in the quantum industry, and that's diversity. Diversity has many benefits, as we all know, in terms of improving the creativity and productivity in a company. But it's becoming a real challenge for the industry as a whole. So one last question for the panel is, how can we improve diversity in the quantum technology industry? Perhaps Biliana, would you like to start?
Look, I think there's no doubt about that. We need to really increase the number of women in STEM and quantum. I think everybody agrees on that. But I think it's also important to understand that there are currently women in the field who have already self-selected. And we need to make sure that they stay there, develop mechanisms to ensure that they don't, that they don't leave. And find ways, as a company, I guess you have to take a stand and decide what do you stand for, stay true to your ethos, and develop ways to measure your progress and have periodical sanity checks. But what I do also want to mention is that, like Jack Nicholson said in The Departed, nobody gives it to you, you have to take it. And so you as women, we have to seek out these situations, seek out opportunities where we can have an opportunity to show our skill set, raise our profile. Sometimes we have to go outside of our comfort zone. I mean, hello, but it's really, really important that we take that initiative. And another thing that women should be thinking about is if you're already in the quantum field, if you're already out there in the workforce, you have actually earned a seat at the table. And so you have to show up to work with that mindset. You have to show up to that meeting with that mindset. You have to write that email with that mindset.
Does anyone want to offer a perspective from academia as well?
Yeah, I guess, so I mean, we actually, seriously discussed whether we should even, ask this question in this panel. I mean, obviously here we have, from the academic side, 4 middle-aged white men.
Speak for yourself.
Middle-aged.
Oh, come on. Sorry, you're already there, Chris. But I think it's really important that we ask. It's a hard question. There's not an easy answer. But it's important that we ask this question, and from the university academic side, to think, what can we do and what are we doing? And I think, if I start from the kind of local area, most local to us, where sorts of things that I'd like to try and do, or we'd like to do, and see whether we're, and a really important thing is we have to listen. We have to keep listening as we do all of this stuff. There's no point in just going, oh, we think this is how to solve it, and just do that. We have to keep listening, because we're not the people who are, like, we need to make sure that this is actually working for the people it's supposed to work for. And diversity, gender is a massive problem in quantum, but there are lots of other diversity issues that we're getting. Indigenous people, the general cultural diversity. So starting at the top, we've got, like, at universities, there's kind of we have to think about what culture we want to create. And you know, we know that funding is in a really constrained environment at the moment. And if you want to try to adjust the balance of, for example, gender, you'd like to be able to hire more women, but if you replace people who were there, then this is a slow process that takes many, many years while you wait for people to leave. And if you want to try and just add more women, then it requires significant expansion and COVID and blah, blah, blah. This makes that all really difficult. But what we do need to do, I think, is think about when we are making those decisions, that is a time when we can influence this. And we have to think about what tools are we using to make those decisions? And how do we measure people's success? What do we mean by success? How do we judge other people's success? And we have to think carefully about what metrics we use. Universities love metrics. Scientists love putting numbers on things. But just because you can put a number on it doesn't necessarily mean that number is fundamentally useful. So for example, judging how many papers people have published. When we're judging candidates in the room, we have to remember that the metrics that we are using are estimating are not just a product of someone's talent, but also a product of luck, huge role that luck plays in your career, and opportunity. And when you're appointing someone, you're trying to judge future success. You're not trying to judge how good their opportunities have been. You want to know, if I give them this opportunity, who is going to create the best outcome? So this is something that we can do. I mean, we have to make this, we have to try to drive this cultural change at universities. But in the shorter term, I think we have an issue with gender diversity. So you can't just put advertisements out there and hope that people are going to come. I think you really need to go out and get people. You need to go out and find people that you want and really try to nurture them and bring them in. And there's lots of ways of doing that, but the undergraduate path that Chris was talking about is a really important one. The last few years, the Sydney Quantum Academy, also some of these centres, the Centre for Engineered Quantum Systems, have been running summer projects. And I've had 3 or 4 female students coming and do summer projects in my group in the last couple of years. And this has been fantastic. And these students have been fantastic. And I really hope this is a longer term approach. It doesn't solve my problem now, right today, but I hope that over the next couple of years, these people are going to turn into PhD students in my group or someone in industry or whatever. And the last thing is that we can't solve this problem completely until we also go out and really change the cultural mindset that STEM is or is not a place for women, or is not a place for Indigenous people. And we need to, and that's where we need to get out with the science outreach at every opportunity and talk to primary school students, talk to high school students, talk to their parents, talk to the school administrators who are advising people on career outcomes, and say, anybody can do this. And not only can anybody do this, we actually really desperately need and want people to come in with different perspectives. Liliana talked about the women being here who have already self-selected. But in some sense, to get through in the current system, that is a selection process of a certain type. And we miss out on so much talent that comes with really different perspectives. And that's what we really want to be trying to capture, I think.
Unfortunately, we don't have much more time for that really important question, but I think you really spoke quite eloquently. And I think everyone here on the panel agrees it's like a real challenge that we're working on, but it's great to hear there is a lot being executed right now to try and change it. And I'm sure we'll continue to try and come up with new ideas to solve it. If we can try and get a quantum computer to work, I'm sure we can tackle this problem. So now we'll move on to the final section. So I've put up a QR code. It's also available on Zoom for those who are following online. Just get out your cameras and look at that link. It'll give you the ability to submit questions to the panel. We'll use the last 10 minutes we have here today to address any of your questions. I think I'll start the first one. So I've got some pre-compiled from before with the invite. This is probably for Simon, because I think I might know what the answer is. What's the most important thing in quantum tech that's not being talked about as much as it needs to be?
Oh, geez, what's the most important? I don't really, that's a good one. I really don't know. There's a whole bunch in quantum tech that should be talked about, but isn't. I'm not sure which one's the most important.
One example there.
Well, we still have a problem with managing expectations. We've been talking about it for 10 plus years. Manage expectations are all getting into trouble. And in some respect, I think it's getting worse. Whether this is a function of the massive increase in corporate involvement, or whether it's the startup community and the investment community getting in, I really think we've gone a little bit downhill. And, you know, some players are worse than others. I won't name any names, IBM. But we really have a hard time when it comes to, and I suppose I just did what I'm going to criticize by having a go at somebody, which I probably shouldn't have done. So yeah, managing expectations is still a real issue. Now, we have been seeing a subtle change in language coming from most notably Google, but PsiQuantum's done the same, and we're starting to see a shift. So we've been dealing with quantum computing, especially sort of NISQ, this sort of near-term, small-scale chipset stuff, which was always a bit tenuous from a scientific perspective. Basically, you have to get quantum computers to a certain size, and to get quantum computers to that size, you need error correction, which means you need a lot of qubits to do interesting algorithms. And there was this push early on of what could we find that was like a killer app using, you know, 50, 100, 150 qubits in any given system. But that question was floating around in 2003, 2004, when I started my graduate degree, and we never found an appropriate answer for it. Luckily, we have been starting to see some language changes that are sort of pushed by the corporates a little bit more to say, no, look, we really are dealing with large scale machines for these things to actually become useful. And maybe that will help change the zeitgeist a little bit and sort of, again, put people into a more realistic framework of what's going on quantum. Certainly my interaction with the VC community has been quite interesting. When they sort of started getting into this in about 2015-ish, 2014, 2015, when you started to see more VC firms getting interested in quantum technology, and it's a consequence of how the Valley works. I mean, they really did look at it as just another app, rather than it's the app and it's the phone and it's the telecommunications grid and it's every chipset that you put into the phone kind of technology. But that's slowly coming around. The more reputable quantum startups out there, they've done a much better job at managing expectations. But you know, the snake oil salesman, you've always got to watch out for. And because the industry is not very big, I mean, for example, those of us, me and my partner at HBAR, we can pretty much manage the entire ecosystem at the moment. It's not large enough that it's just things that we can't keep track of. We know most of the companies, even the new ones that come along. It's still very, very small. But the problem with that is the snake oil salesman can have a very large impact that needs to be pushed up against and needs to be managed by the reputable startups and the reputable corporates. So I wish that would accelerate more. In some sense, it's getting better, but I'm also worried that it is in fact getting worse.
Maybe I'll add, I'm not too concerned about the impact on investors. I'm not too concerned about a little bit of this inside baseball of what's going on in our community. I am concerned about geopolitics. And quantum technology comes up a lot in geopolitics. And the reason for that is that the upside potential is enormous, both in technological capability and potential financial gain. It is extremely difficult to understand for almost everybody, right? Especially a lay audience. And certain nation states have made this a public priority. Now, when you combine those things with what Simon was just referring to, which is the fact that it's easy to craft false narratives or narratives that are misunderstood, we see that people who, manage fighter jets and decide where army battalions are going to go, they get misinformed by some of these geopolitical considerations. And that really terrifies me. I had a general not long ago explain to me, it's an Australian, retired Australian general, explained to me, like, wax poetic about how China has this unbelievable stealth defeating quantum radar. And it's what it really is China made a national priority out of investment in quantum technology. It is a real strategic research priority. They made some questionable pronouncements in state media that were designed really to shake things up. And the Western media ate it up. And it's just fundamentally untrue. This technology doesn't exist. And actually the same week that this general was waxing poetic to me about it, the inventor of the concept, a guy at MIT named Jeff Shapiro, wrote an article about how quantum radar doesn't and can never work, right? I mean, but that concern has infected the people who send men and women to war. That to me is actually quite terrifying. And it is an area where I think that taking back the narrative and keeping it tied to reality is actually a responsibility for all of us.
I'll just remind everyone, you can actually upvote things that you're most interested in hearing about. So I also recommend that everyone jumps on and just has a look at what questions are available. So this one I'll leave open. This is a big question. How will industry address the potential nefarious applications of quantum computing? For every noble quest, several are determined to use these developments for not necessarily the betterment of mankind. Anyone want to take that one?
I mean, I'll go, but go ahead.
Well, I guess one thing that I would say is that at the moment, the whole industry academic space in quantum technologies is in a bit of a kind of a luxury state, in the sense that industry is really desperate for academic involvement and to be benefiting from academic results. And they're also really keen to share what they're doing. So there is a lot of what's happening in quantum technologies that is still really open research and public, and where companies like Google and IBM are taking their systems and publishing papers to discuss how they're doing, what the outcomes are. So one of the things that you can do is just shine the cold light of day on these things and make sure everything is out there in the public domain. That helps. Now, of course, I don't know how much stuff is going on behind closed doors. Maybe we're just seeing the tip of the iceberg. Who knows? But I think that actually at the moment, the vast majority of what's happening in the quantum technology space is in the public domain, and that I think really helps with that.
Liana?
I was going to say one of the things that we've started to really think about is responsible quantum, and how can we actually get together now to sort of help, I guess, learn from what we've seen in AI, learn from what we've seen in biotech, and can we figure out a way to position ourselves better? And we're taking initiatives to actually lead that conversation later this year. But I think really thinking about identifying some of the risks, understanding and prioritizing those risks, and based on impact to society, impact to, what have you not, because this is not a technology that's coming tomorrow. So we do have some time to, still think about it and think through the implications. And I think understanding which risks are emerging, which risks are just make-believe right now, and start addressing them through conversations through responsible quantum regulation, policies, and what have you.
I mean, I'll say, I'll take a slightly different view. Anything worth doing can be turned into a weapon, right? anything useful can be turned into a weapon. And I think it is valuable that people think about the counter-proliferation questions. How do we ensure that there's ethical development of the technology, that we, protect personal data? I think it's useful that people think about that. I don't think it's useful that it becomes like everybody's responsibility is ethical development of quantum technology. Like we don't know, right? We don't know what that looks like. It's also not an area of expertise. And I think you do see that there have been failures in, say, conventional AI that was just brought up about algorithmic bias and things. They were in part identified by parts of the community who are specialists in like wielding technology for good, in air quotes. And I think that the lessons we've learned there, that supporting people who want to pursue these questions and want to proactively come up with solutions, that I think is a very good way of approaching it, as opposed to the more simplified version, which is everybody has a responsibility for building ethical frameworks and stuff. Like I don't know anything about ethical frameworks in technology, but there are people who do. And I would strongly encourage them to be supported to come up with potential solutions that others can implement.
Could I just add that I think one of the ways which we can combat this is probably the same answer to how we combat it in conventional technology. That's education, not just of people in the field, but of everyone, so that everyone understands what's at stake. Otherwise, a government or a company can just craft their own narrative and tell the users of their product that the government's wrong, or the government can say that someone else is wrong. And if the population has no clue one way or the other, and they just trust what's coming through their feed, then it doesn't matter what we do, in a sense, in the field. So everyone needs to sort of understand what's at stake. And I think that is going to be a huge problem, because not everyone even understands what happens when they click accept when they turn on their phone for the first time. And then when it comes to giant important policy decisions, people are lost, and they don't seem to actually care. So I think educating people on what this technology does, what it's meant for, and how it connects to what's important to you, your values, your needs, is going to be, it's important now. We're not doing it now, but it will be important for quantum technology as well.
I think we've got time for one last question. There's been quite a popularity around basically students asking questions about the quantum industry. I've summarized them in sort of two ways. One is, how are we going to convince students to join the quantum industry, considering it's so small, and that there's been statements about those students then being poached? And then if you are a quantum student, what do you think they should be studying? And then finally, if you're not necessarily a quantum student, do you think is there a position for people without quantum degrees in the industry as well?
Well, students are already very, very enthusiastic about doing it. We see it at UTS in the engineering and IT faculty. We have internships going, and we always get a huge response coming from students who aren't trained in physics, aren't trained in quantum. So there's always a place for them. Certainly, I'm sure Michael will say more about it. What fraction of the Q-Control team has a background in physics and quantum? I assume it's not the majority.
It is, but I think maybe, sorry, that was not fair of me. I think to your point, it is important that Q-Control is approximately 50-50 people with quantum backgrounds. We do operate the world's largest team of PhD level quantum control engineers, and people with product background, people who have never ever worked in quantum before they came to Q-Control, people who are web designers and graphic designers and user interface designers and web developers, all these things. So I think there are many, many opportunities. And if you want to upskill, then I'll promote this thing that Chris and Q-Control are doing together. It's a product called Black Opal. It'll be out soon. It's like Duolingo for quantum. You want to get up to speed, it's a great way to do it. But we also are very keen on just advertising that, man, if you come from a background that's peripheral and you want to work in this industry, the salaries are outrageous. Like the amount we pay people is ungodly. Watching my budget like vanish every month in the bank account because it is in demand from us as employers. We want people to come into this, and that's on the technical side and on the more producty side. So it's a great industry to get into.
Yeah, and the other thing is like there is a massive demand for people with quantum expertise worldwide at the moment, at universities, but also in all of the industry players that are involved. They are all looking for people, and a lot of these people are going, we need people with quantum training, and it's really hard to find them. Microsoft in Sydney, I've heard people from Microsoft in Sydney on many occasions go, like, we want people with more training. We will partner with organizations who can help us get people in who have more training. So if you choose as a student to do a technical degree that has some quantum technology involvement and some pathway into quantum, your technical skills at the moment will be very much in demand. And that's just for the people who end up inside quantum. And as we said before, the sort of stuff that you learn, the sort of deep tech skills that you can learn on how to merge leading science with complicated engineering and industry type development. These skills are in demand everywhere. I mean, they always talk about how people with physics backgrounds end up getting employed by consultancy firms. It's not because they know how to solve Maxwell's equations. And the same thing will be true here. If you get training in some sort of area of deep tech where you've shown that you can master some like deep science, and at the same time the kind of engineering and industry type component, I'm pretty sure that in many different areas where those things are important, they're just going to want to lap those people up.
I was going to say, for those who don't want to necessarily stay in academia or who don't want to be a deep tech people, there will be opportunities for you as quantum consultants. There will be as quantum product managers and product developers. I'd say to the questions of what subjects or what to study, try to sprinkle some psychology and communications into your highly technical degrees. Do some public speaking or things like that, so you can actually be the translator, be the go-between between the various sort of ends of the spectrum, because I think those people will be in high demand.
I'll just point out that if you come to UTS and you come to learn quantum at the undergraduate level, you're not a quantum person that's pigeonholed in quantum technology, right? You're an engineer, and on top of that, you're a computer scientist, and 10% of the courses you took were in quantum. This is what a specialization is, right? This is all specializations, whether you come and specialize in data analytics or machine learning or architectures, computer architectures. Whatever the specialization is, that's 10%. You're an engineer, right? But you have this specialization, and so you can come and you can study this exciting field that gives you lots of a breadth of skills that you won't be able to get anywhere else, that you can apply outside of quantum, and it's exciting.
And I would just say, like, what you should study, as well as studying all those other, basically, I think you should study the thing that you love the most, because it's so much like quantum is so interdisciplinary. You can kind of hoist anything into it. If there's something that you really love and you really like the idea of quantum, study the thing that you love and work out how to get that element of quantum in there, whether it be through engineering or through finance or through chemistry or whatever, because there is a pathway there. We're trying to work on that in the Sydney Quantum Academy as well, but there is a pathway there. Do the thing that you want to see. We don't know, like, we came the boring path into quantum. We don't know what the interesting paths into quantum
Again,
are.
speak for yourselves.
But like, we want the new people to show us what are the interesting combinations that they can put together.
They have, just really quickly. I just finished teaching last semester, Introduction to Quantum Computing. And the students, what they did to learn their first subject in quantum computing was they built a quantum video game. And they taught me things about quantum computing that I didn't know, I couldn't have thought of. it'll be showcased. I'll write a blog post about it, but it'll be showcased later. And you can see quantum tic-tac-toe and a quantum music box and all sorts of interesting applications of quantum technology that I guarantee you Google and other people aren't thinking about.
Yeah, I think that's a really great positive way to finish. A lot of opportunity and clearly a great space to be in. So I highly recommend everyone listening to get involved. So that finishes the main section. Let's thank our esteemed panel. For those online, you can log off and have a drink. And for those here, we've got a bar open if you want to jump on. Sarah, do you want to say anything fun? No, great. So please stick around and say hello to all of us. We'd be happy to have a chat. Thank you very much for coming.